Hello, everyone, and thank you for joining us today. My name is Lou Parrish, and I will be your host for this webinar on the wastewater treatment and ammonia recovery system technology sponsored by NASA's Technology Transfer Program. In my job as a Senior Technology Transfer Specialist, I support this program and work with NASA scientists who have developed new technologies that may have applications outside of the aerospace industry. We patent these inventions and market them to industry through our website, which I'll show you later, as well as through efforts like today's webinar. Our presenters today are Griffin Lunn and Oscar Monje. I'd like to give you some background on our presenters. Griffin Lunn is a licensed chemical engineer in the state of Florida who has worked at Kennedy Space Center since 2008. Griffin has worked in various R&D and facility design jobs for various government contractors, supporting Space Shuttle, the International Space Station, and the Artemis program. His research interests include environmental control and life support systems, focusing on water, air, and bioregenerative approaches, as well as in situ resource utilization for crewed systems. Griffin's specialization in pressure vessel and process piping safety and instrumentation and controls helps enable the construction of high-performance test stands to evaluate unit operations, enabling sustained human habitation beyond low Earth orbit. Griffin currently works for Bennett Aerospace Incorporated under the LASSO II contract and has a Bachelor of Science and Master of Science degrees from the Florida Institute of Technology. Oscar Monje is a research scientist currently working for ATOS under the LASSO II contract. Following today's technical presentation, I'll be giving a short presentation on how NASA's licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have questions, please type them into the chat box, and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to Griffin and Oscar.
Thanks, Lou, for the introduction. Could we get the next slide? So, me and Oscar are here to present to you guys some of the work we've done at Kennedy Space Center over the last almost 15 years. Could we get the next slide? So today we'll be going over our initial problem statement that led us to this innovation, how we solved it, go over more of the chemistry cycle of it, the advantages and the challenges of this process, the terrestrial applications that we're aware of, the commercialization status, and some further developments. And then Lou will have a section on how to license this technology. So we can keep going. So on the International Space Station, we don't like to talk about this much, but urine recovery is a very important process to enable long-term habitation. And currently we recover urine by taking crew waste, the urine stream, and running a vapor compression distillation on it. And recently we have a new unit on there to allow brine dewatering, to allow closer to 99% water recovery. This combined with the humidity condensate allows the majority of water to be recovered on the ISS, saving them hundreds of millions of dollars a year. But for longer duration journeys, higher water recovery will be needed due to the upmass and the cost per upmass, with current upmass being about $50,000 per liter. And due to this vapor compression distillation process, we use a pre-treat on urine using a chromic acid oxone mix. I think some phosphoric acid now. And due to this pH, the low pH, this keeps the urea stabilized and it allows them to distill it without getting any volatiles off on it. However, urea polymerizes with water to form a wax during terminal water recovery. And even with chromic acid and oxone and all those pretty nasty chemicals, some microbes are able to grow in it, and I call it spoils the batch. It causes the urea to break down into ammonia and CO2, and the current system cannot tolerate ammonia recovery. Essentially, it prevents the water from being recovered, and it ruins the batches of dozens of liters. So removing urea in a purpose-built system to get the CO2 and ammonia, that allows higher terminal water recovery to be achieved, and it also enables more different water recovery technologies to be used, especially membrane-based ones, which are normally not selective against urea. So in the architectures I've developed over the last decade, we prefer to have a carbon and ammonia removal step. The question was, how do we do it? Next slide. So the solution me and Oscar and others stumbled upon is that when we were building bioreactors, we followed a traditional earth-bound wastewater treatment process of using nitrification, denitrification. So we use bacteria along with carbon oxidation bacteria, which are most of them, to break down urea, use it as food, and for them, and break it down into ammonia and CO2, and then terminally take that ammonia to nitrify it to nitrite or nitrate, and then denitrify it to nitrogen gas. That process is very slow, as people in industry know. It takes, for us, it took days of contact time. We got it down to dozens of hours, but it's a very slow process, and the bacteria nitrifiers are pretty delicate organisms due to the low energy of the ammonia, that as a terminal electron acceptor, ammonia is just not that much energy, therefore they don't grow that fast. And they're very delicate to perturbations, and they're delicate to pH control as well. And if they aren't eating well enough, the carbon oxidation bacteria will eat them. So it's a delicate setup, and we're high strength wastewater. Wasn't very good for them. They could do it, but it took a long amount of detention time or residence time, and then it was not the most consistent process. So we looked for a physical chemical solution, and the inspiration came from our pumps. So when you run recycle pumps on a bioreactor for this waste stream, human urine, we noticed that there was a precipitate in the pumps, and anyone who works at wastewater treatment plants would see this as well. It's called struvite, magnesium ammonium phosphate hexahydrate. And this is also found in urinals as well. That's why they don't flush as fast. So with this formation, we were like, why don't we have a reactor create the struvite to remove these minerals from the wastewater? And in back 10, 15 years ago, this was an area of study. It was just done with a different method. So they used something called a magnesium precipitation method. But for our wastewater stream, we have a 1 to 10 to 1 ratio of magnesium, ammonia, phosphate. So for like a sludge dewater, their ratios are more like 1 to 5 to 5. So for our waste stream, we're like, adding magnesium alone won't do the job. We need to add magnesium phosphate, and there are many magnesium phosphate minerals. And we did a study, and then there's this one particular mineral, nuberylite, which is used as a food additive, as the E number, magnesium phosphate dibasic trihydrate. And there was some data from Japan showing it does react with ammonia, but at very slow times. I think they were doing contacts in hours, and they were getting some surface chemistry on it. But when we ran our novel pre-treatment process on the mineral, and we ran it at a proper pH range, we found out in one of my papers on this with Oscar and Dr. Baron Tanzel, is that pH is very important for this mineralization reaction. We're able to get the conversion of nuberylite to struvite down to milliseconds of contact time, like on the order of hundreds of milliseconds of contact. We were getting ammonia absorbed to the solid, and we were getting solid utilization of over 50%, probably closer to 75. So this correlates to, by molar weight, 5% of the nuberylite could absorb ammonia, which is much higher than any ion exchange resin, because it's just a simple reaction. The active site is the whole particle. So we thought at the end of the day, that's all we need to do. We have essentially a one-time use absorbent that absorbs ammonia very selectively and sequesters it to allow the wastewater to be distilled or separated into water at a high purity, high recovery rate. We thought our work was done, but Oscar here was like, you want to tell the story?
Yeah.
Okay, I'll tell it. So Oscar's like, why don't we regenerate it? And I'm like, looking at Wikipedia, my favorite thing in the world. It's like struvite decomposes at 400 degrees C. That's what Wikipedia says. Oscar says Wikipedia lies. And we found out they did. So struvite does decompose at 400 C. That's a real reaction. It'll decompose into its constituent elements. Oscar has a zeolite regeneration test stand that only ran to 200 C, and he ran it anyway because he does whatever he wants. And with that, he showed that within 15 minutes or so, you were able to get the majority of the ammonia off the struvite to return it to Nuberlite. And you had a FTIR unit that could tell us the water peaks and ammonia peaks. Not many people have this unit. And we were able to see at certain temperatures, when does the ammonia come off, when does the water come off, and it comes off in little steps. It was pretty neat. And he kept going lower and lower in temperature, and it at 100 C it regenerates, below 100 C it regenerates, and even at room temperature it can regenerate when you apply vacuum to it. So this was not in the literature. And looking back in hindsight, people in Canada noticed when they store struvite fertilizer in the summer in silos, they were losing ammonia tighter. So there's some evidence of it, but no one's built a purpose-built system that could regenerate the struvite into Nuberlite in a reasonable amount of time. This was a very quick process. And later we noticed, we took microscope images. Some of these are below. These were taken by my intern, Andrew Gleich, at the time. He's now at Boeing. He can't be in here because he's in Russia right now supporting the ISS program. The Nuberlite, when it absorbs the ammonia on the left, it gets kind of puffy. So it's dissolving and recrystallizing on the surface. We discovered there's a certain particle range where this is optimized. And we noticed the COTS Nuberlite is not made for this reaction. It's meant as a food additive. We were able to modify it using simple equipment to make it more conducive to this reaction. After cycling the material once or even twice, it gets better. So as it regenerates, the specific surface area increases, but it doesn't increase to like dust. It doesn't. As you increase surface area, your back pressure goes up due to Ergun equation. That stopped happening after a couple regenerations, and the process became more consistent. So if you absorb it and regenerate it, it was able to act as a cycle. And we'll go into the next slide about that. So this is what I call the struvite cycle. I'm terrible at naming things. So there are other struvite cycles. This is Kennedy Space Center's struvite cycle. We exploit this mineralization, demineralization reaction to capture and move ammonia. So this is from our paper with Dr. Tanzel and Oscar, that at certain, this is just one of our images, but we have a whole more or less phase diagram of based on temperatures and pHs and reactions, you can get different magnesium phosphate minerals. There's also one called struvite K, which has potassium. We'll get in that one later. And so with all these minerals, and other minerals do not react with ammonia in the same manner. So it's only Nuberlite that does this. So and this is a little figure we had. I think this might be in the patent, but this is the application using coke oven gas from a coal plant. You would take the gas. You would essentially water strip it with water to accumulate the ammonia. Ammonia is going to be soluble in water, and then you run it through a column. And let's go for step 2 right here. I'm not sure you can see my mouse, but on step 2 on the left, you have a column that's fed in an upflow configuration. It can do both. But water and ammonia goes in, and this is pre-dosed at a certain pH. It's called that pH influent. This is a very special number that's calculated as a function of the ammonia concentration. It essentially solves for an ideal pH. And there's a range where this pH can be, and it's very important. And it's a function of concentration, which has a range where it should be. And with that ammonia concentration, it goes in and it contacts virgin MP, and then it will convert into MAP, and essentially at the front of the reactor to the back of the reactor. It's called a breakthrough curve. So mass transfer happens and it absorbs it like an ion exchange resin. And once you get breakthrough, as in there's no remaining, the mass transfer zone of the MP to MAP is larger than the remaining MP. That causes leakage of the ammonia. You get ammonia out the top. Once that happens, you can sense this with like pH and ammonia sensors, even conductivity sometimes. Then you take the column out of service, and then you apply steam or heat or vacuum, any combination of those. And with a sweep gas, preferably, ammonia is released into the sweep gas. Sweep gas can be air or nitrogen. It doesn't seem to care. And the ammonia is released as a wet ammonia, essentially a dilute ammonia hydroxide solution, around 25%. And with that, the MP is returned to its initial setup, and you can continue stripping more ammonia. So it can remove ammonia from a wastewater stream, and then it concentrates it, and it removes other organics, microplastics, anything like that. And it's a concentration tool, and it allows recovery of ammonia. It doesn't destroy it at all. And it ignores the organics, it ignores other minerals. There's in very limited forms, it can absorb potassium, but we figured out how to avoid that with careful pH control. And this is the drawings here with time course over breakthrough. Yeah, I just love the graphic designers. They can draw this up. I can't draw anything at all. So you get a breakthrough curve here, and the whole system has a continuous water stripper for gas. This is just one implementation. You can have a wastewater source as well. And then you're constantly removing the ammonia and concentrating it with we call this a merry-go-round or carousel configuration, where you have multiple columns going in absorb configuration to regeneration configuration. And the ratios depending on your on time for absorption over your on time for regeneration. The high concentration systems, absorption can deplete a column very quick because the reaction is very fast. Some of the columns have endurances in minutes because they're not kinetically limited, that it will absorb as quickly as possible. And then regeneration, we've gone down to about 15 minutes, but on larger systems, you get to heat up to your temperature, and that's your heat transfer limited. So you might have multiple columns absorbing, but only one regenerating at a time, for example. The very dilute waste streams, you'll have probably a lot of columns. Columns will be absorbing, but they'll be absorbing for hours, if not days. And then regeneration is a transient that keeps one column out of service at once. We can go to the next slide. So the advantages of this technology are, it's to our knowledge, it's the fastest removal technology for nitrogen. And I'll mention phosphorus here, but I'll get into that in some of our questions. But this technology can also accumulate phosphate. We call this breeding. But this is the fastest removal kinetics for nitrogen as ammonia or phosphorus known. So what do kinetics enable? They allow the smallest volume to treat a unit flow. Smaller volume, with all other things being equal, allows lower capex and plant footprint. So some of the largest wastewater treatment plants in the country are hundreds of acres, like Stickney plant in Chicago. I think it's over a square mile. And like Deer Island in Boston is most of that island. So wastewater treatment, especially in like island societies, like and like military installations, you're space limited, and this technology can take a very small footprint. Can fit in shipping containers. And besides the kinetics, it's also extremely selective for N and P. It doesn't add anything besides residual struvite. It's slightly soluble in water. So you're limited on your effluent conversion to about 10 ppm, maybe down to 5. We've been getting lower and lower. That's a control issue. But it will not absorb it will not foul with other ions. It ignores sodium. It ignores potassium when run at the right pH. And even when not, its selectivity is still 10,000 to 1 for nitrogen as ammonia. So it's extremely selective. It ignores organics. It's more or less temperature insensitive. It works as well cold as it does hot, unlike bacteria, which have a growth rate as a function of temperature. In the winter, they don't work as well. This process does not care. Besides, nitrification doesn't allow the recovery of nitrogen. It destroys it as nitrogen gas. This technology allows the recovery of a wet ammonia gas that you can be converted to fertilizer products. And if you breed media, as in you're creating more struvite over time, you can also harvest that as additional struvite, which is a bit out of scope of the patent, but it will just happen. So this is a potential profit center for wastewater treatment plants. We believe the ammonia recovery will pay between 50 and 75% of the wastewater treatment cost for that step. And then phosphate recovery should allow it to be actually profitable at that point, with phosphorus selling for a lot more of an ammonia per ton. And besides that, we have a lower alkalinity requirements, which is the main OPEX cost for nitrification. than most technologies. Instead of 7 milligrams per milligram ammonia, and it's closer to 3 what we found, but more data is needed. And the other main energy driver is aeration. So for nitrification, you need aeration. You need to force oxygen to the bacteria because they're aerobic species. They need oxygen to convert to nitrify because it goes from ammonia to NO2 or NO3. They need oxygen. We don't need oxygen at all, but we do need sweep gas. But sweep gas is run on the media and not the bulk liquid. Far less gas is needed and far less pressure is needed because I'm not aerating acres of more or less ponds or tanks. We're aerating a vessel for minutes, so not even all the time. So it's lower aeration costs. These costs combine. Wastewater treatment uses between 1% and 2% of all energy in the United States and other first world countries. Aeration basins for secondary treatment, which is removal of ammonia and carbon, it uses about half that energy. So this is about 1% of all energy use is from nitrification. So if we can lower that energy cost, that's a big difference. That's taking power plants offline in the grand scheme of things. It's a lot of energy. It's a lot of cost. And this media, instead of like a special ion exchange resin made out of plastic, it's a commodity chemical. It costs $1 a pound. And in some processes, it's not consumed. If you're doing like purified water treatment, you will consume the media, but in like sludgy water, you will gain media. So you'll be able to breed media. You can make more reactors off of what you breed. And this breeding you could double a reactor size every week in some configurations. And you can sell this media for about $2 a pound nowadays. So struvite's more valuable than nuberlite. You can keep going. So now this isn't perfect. So we have some challenges we've been working on. And due to the kinetics, the contact times required, because of the control loop of the pH in and out are both control points, the flow rate and the contact time is actually set by concentration. You cannot go, in most configurations, you cannot go below that contact time. So that requires a certain contact time. Sometimes the contact time's in seconds, a couple seconds, under a second in some configurations. So that requires a lot of back pressure due to Ergun equation. You have a particle size, a packed bed of a certain length, a certain contact time is going to cause PSIG of pressure drop. Unlike nitrification, nitrification runs off inches of water column. You can run it off gravity if you wanted to. We run at higher pressures, not at like hundreds of PSI, but we're in the dozens of PSI. We're still in the realm of using PVC to build this, but we're at the cusp of what PVC can take. PVC doesn't really like above 100 PSI. So we're at higher pressure. That requires a supply chain to move the wastewater at a bit higher pressure. So the plumbing vessels and the pumps are a bit different. They're not what people are used to. It looks more like a chemical process than a wastewater process, in my opinion. And the media precipitation, because we're converting a nuberlite to struvite and back and forth, based on pH control, you can cause variable back pressure. So the control algorithm is a bit more complex because you're solving for flow rate based on the titer of the inlet ammonia, which gives it a inlet alkalinity dose that causes it solves for the flow rate, and that will generate an outlet variable of back pressure. And if that back pressure builds up so much, even if the column isn't spent, you have to regenerate it to lower the back pressure. And we've noticed, luckily, that every time we regenerate the column, the back pressure resets. So the media it'll amalgamate and it'll break up. And if we run it correctly, it will do essentially the particles will erode and dilate. When they build struvite, they'll grow in size. When they regenerate, they shrink in size. We're not making too many new particles, and we're not destroying particles. We're keeping them the same, or we're keeping their particle size within a range. They do stick together when they're run in correctly, and that can cause bricking. And regeneration, as long as the gas can pass through it and heat up, it will reset the column. So it's a bit more difficult than nitrification. You just let them grow and they do their thing. We have to be careful and we have to monitor this process. So that requires a high instrumentation. We need pH and ammonia probes. Ammonia probes are not cheap. The one I was using was $10,000, for example. The control loops are very fast. This process is very dynamic. It's a fed batch reaction, and the columns might only last a couple minutes in service. So your control loops are running one or multiple times per second. A bit different than wastewater, which you can run stuff on a minute scale. And the operating conditions are based on live influent conditions. So you need a dosing tank and you have to measure it correctly and then dose according to it. So buffer tanks are needed to get the tight pH dosing that this process requires. And I don't require it, the chemistry requires it. The physical laws of this process requires a very narrow pH range to run correctly. And as ammonia is removed from the column, the pH drops in the middle of the column. And what our patent does is show that if you control the effluent pH based on contact time, you can remove so much ammonia per pass. And then you take that effluent, you redose the alkalinity back to the high pH and run it in again. And that allows quick terminal ammonia removal. Once you get below, say, 100 ppm ammonia, you can do this in one pass. You can remove about 100 ppm of ammonia N, from the high pH allowed before it can't get too high or it'll amalgamate to where it gets too low where it starts dissolving the media. And if these aren't respected, if the pH gets too high or too low, the process becomes harder to repeat. So it's very important. For example, you can't let the wastewater sit in the reactor. You can't turn it off, but you have to dry it out and then let it sit. So it's a bit more finicky, but in exchange for this, the performance is orders of magnitude higher than other processes. So it's I call it high risk, high reward. And some terrestrial applications, this is what we have discovered. If licensees come to us with their own applications, we don't mention them here because those are their applications. But the obvious ones are decentralized wastewater treatment, municipal wastewater treatment, industrial wastewater treatment, decentralized fertilizer production from this wastewater treatment, and then other applications licensees bring up. And it brought me up some crazy stuff, and I just didn't know it was a thing. So I'm not going to spoil them, but be creative. There's ammonia wastewater in a lot of places. Go to next slide. So further developments we're working on, like the licensees are working on. I'm doing other things right now, but licensees are in very vague terms. They're trying to design, construct pilot plants for influent evaluation. A pilot plant could be like the size of a refrigerator. It could be the size of a shipping container. It's just bigger than a lab setup. So they're building pilot plants to evaluate the influent to see if it's suitable for the figures of merit we promise. Once you go from there, they're going to be scaling it up to demonstration plants. And this will allow the building of modular reactor skids for deployment to test other applications. Each application is going to have its own quirks. You might need a certain pre-treatment regime. You might need a post-treatment regime. Wastewater treatment is complex. So this isn't a one-stop solution. It's a tool to allow wastewater treatment designers, EPC firms, to treat wastewater in the most effective way possible. And with this data, there are trade studies comparing technology to this data. I have some basic data on that. And then from there, licensees are working on improved reactor designs. We provide a reaction. We provide chemistry and operating conditions. How the reactor is built is up to the licensee, and they have some different designs. Keep going. And I would like to take this time to, so me and Oscar are here. We have 4 inventors here. We had 2 interns who helped us out on this project, and they're listed as inventors because they did the work. And that's Andrew Gleich and Julia Worrell. And I don't think any of them are with us today, but yeah, and they're both at JSC actually, and Andrew's assigned to Russia for some reason. But we had Dr. Tanzel at FIU and Dr. Lee at UCF help us through Florida Space Grant. NASA has funded us multiple times through the CIF and IRTD funds. And as I said, Florida Space Grant Consortium helped us out. That was pretty fun. NASA KSC Tech Transfer keeps inviting me to things, which is nice. And I would especially thank our previous and current licensees because they believe in us and they try it out, and they're the tip of the spear trying to figure this out. And yeah, it's always fun. And I think now we got loose slides, right? There we go.
All right, thank you, Griffin and Oscar. We've received some questions during the presentation, and we'll get to them shortly. But first, I'm going to give you a brief overview of NASA's technology transfer process. To access technologies like the wastewater treatment and ammonia recovery system that Griffin and Oscar just described, you can search for them using NASA's Technology Transfer Portal. All of NASA's patented technologies are listed in the portal at the website shown at the bottom of the slide. You can see NASA has quite a few patents available in a lot of different categories. Okay, here, next slide. When you go to the portal website and begin to scroll down, you'll come to the section shown here that allows you to search for technologies using keywords. Like right here where we put water treatment. Okay, here, next slide. Once you enter a keyword, you'll be taken to a new page that provides you with the results of your search. In this case, the keywords used are water treatment, and the wastewater treatment and remediation technology shows up at the top of the search results. To see more information on the technology, you click on the Read More link below the technology. Okay, here, next slide. After clicking on Read More, you're taken to a new page that provides a description of the technology. This is only the top portion of the description, but the Ask a Question and Apply to License links at the top right of the page are important and will be mentioned again shortly. Next slide. As you continue to scroll down the technology description page, at the bottom you'll see a download fact sheet as a PDF link, which is highlighted here. Clicking on this will allow you to download the full fact sheet. Next slide. This is what the downloaded PDF file for the fact sheet looks like. You'll see that it includes a description of the technology, its benefits, and applications for which it might apply. At the bottom of the second page, there's a contact information for the NASA Agency Licensing Concierge. This person can help answer your initial questions and put you in touch with the appropriate licensing specialist at the NASA Center handling the technology if you'd like to speak with someone to get additional information about the technology and discuss potential licensing. Next slide. If you click on the Ask a Question link during your search, you'll be taken to this page shown here, where you will fill in the information about yourself and your company and ask whatever questions you may have about the technology. This questionnaire will go directly to the NASA Agency Licensing Concierge, who will review your questions and get back to you with answers. Next slide. This slide illustrates the NASA licensing process. Once you find a technology you're interested in on the portal, you can apply for a patent license through an online system called Atlas. A link to Atlas is provided in the technology description, as you saw on the previous slide, where the Apply the License link was shown. Once an application is submitted and accepted in Atlas, the terms of the license agreement can be worked out with a NASA licensing specialist, and the license will then be executed between NASA and the partner. I'd like to mention here, we're going to have a couple of conferences coming up where our technology is going to be featured. One is the Georgia Environmental Conference. That'll be in Jekyll Island Convention Center in Jekyll Island, Georgia, later this month. And in October, we'll be taking it to the Remediation Technology Symposium in Banff, Alberta, Canada. All right, we've gotten some questions during the presentation, so thank you to everyone who submitted questions so far. Feel free to continue submitting your questions by typing it into the chat box. And if you have any questions for me about licensing presentation, I can answer those as well. If we do not get to all the submitted questions today, then we will follow up with you by email afterwards. All right, let's see what we've got here in the questions. All right, Griffin and Oscar, any data related to erosion, specifically salt water? For example, how does this tech perform in areas with high salt or sodium chloride?
So luckily, human urine is very high in salts, including sodium chloride. So that's where we tested it first. And I would say testing of human urine is like the more intense version of this. And we did ICP analysis on the solid. We put it, I think we did EDS, so electron microscopy, EDS. We could not find sodium on the mineral at all, and we don't have a pathway for that crystallization to happen. So this process completely ignores sodium. So that's why it was surprising, because ion exchange resin, it's going to take the ammonia is a +1 cation. It's going to want sodium and potassium. And for our mineral, you can get potassium on there. So you have potassium chloride. You can get something called struvite K, which I thought we discovered in the lab, but someone beat us by a couple years. And so that's magnesium potassium phosphate. That only happens at elevated pHs, like well beyond where we're at. If you keep the upper bound below a certain value, you will not get any potassium uptake. And the potassium uptake is small. We can't regenerate it once it uptakes potassium. It bricks, as I call it. I use brick a lot. But you can't use vacuum to demineralize it at that point, or heat. You need a lot of heat at that point. But ammonia is volatile; it'll come off. But yeah, sodium is, we have not seen any sodium uptake or mineralization, or calcium either. We couldn't find that. We found zero.
Okay, thanks, Griffin. Yeah, is this technology scalable? If so, under what circumstances?
Well, we hope so. But so you build a packed bed column of a certain length diameter ratio. We prefer long, probably over 6:1. And you can either, so we prefer running multiple columns. So in our preferred implementation, this is in our FAQ document. It's available to all licensees, and you guys can request it if you want to license it. But I give a general setup that this is it's a point where all licensees can't complain that they came up with it. So I give a base document that this is the ground technology, just so they can't try to patent that over it. But our main implementation is running influent and effluent tanks. You instrument the hell out of them, and then you run one or more independent columns. We call them reactor skids, and they have their own pump, one pump per one reactor, and they pull from an influent tank that's controlled at the right pH and ammonia concentration. They run their flow rate according to that solution, and then it goes into the effluent tank, and the effluent tank gangs all the effluent reactors from the reactors, and if any of them break through, it will see it on the gross effluent probe. So you don't have to put probes on each reactor. That's expensive. And that's our preferred implementation. That can scale to any size. I did a study for stick meat plant, and I think I could do it in 2 shipping containers for their whole sludge water recycle. That's nothing, and they're the biggest wastewater treatment plant in the world, to my knowledge. So I did a trade study on that, and it wasn't that big. It's a lot of pumping because they run, if I recall, their sludge dewater is over a meter squared. I can't remember if it's per second or per minute, but it's a lot of flow. It's a very big plant. It does all of Chicago land, to be honest. But yeah, it is scalable. And the other concern for NASA is, can we scale it down? Because ISS only generates 6 liters of urine per day. So something the size of, you're running 250 mLs an hour. And yeah, our column size could be 10 milliliters, because you could regenerate and absorb it multiple times per hour. So I say it's under the size of a Coke can. So yeah, it scales down. The technology scales down, and then it scales to, as long as you have modular reactor skids, you get to the point where you don't want to build them bigger, because the parts that assemble them get too expensive. You get outside a commodity PVC range. I think over 12 inches would be kind of bad, just because the parts aren't as available, and they're not cost effective anymore. We can keep going.
Okay, thanks, Griffin. Do these applications follow National Sanitary Foundation standards?
I do not know. So if Ray wants to elaborate on that, I could answer that. But remember, we are one step. So we remove ammonia and hopefully phosphate. Don't touch any organics. So any organics in there, any VOCs, are ignored by this process. It is one unit operation that allows recovery of ammonia and sometimes phosphate. So it's not a one-stop solution, as I said. But yeah, if you can elaborate on that, I'll try to answer that.
Okay, thanks. Could there be an application of modular reactors being used for ecosystems remediation processes?
So I've actually talked to this at length with another company. So the problem is ecosystem remediation. We're talking about 1 ppm ammonia and phosphorus. This technology is really for, I would say the lowest we would go is like 20 ppm ammonia. So wastewater influent is between 10 and 50. The sludge dewater is like 500 to 2,000. depending on how efficient the sludge dewater is. So in a wastewater treatment plant under a MLE setup, you have your activated sludge process, and then they press the sludge. They take the dewater, they recycle it to the headworks, and then they take the sludge and they terminally process it for fertilizer or burn it or whatever. And with that, you get bulk nutrient recovery there, but the liquid is rich in nutrients. So a lot of these technologies look at sludge, dewater, recycle as a source of these nutrients, and for this process, it would be great. But even the headworks of a wastewater treatment plant, we're at the lower end where we could treat it, and that just requires some. The process controls will be a bit different for dilute streams, but that would be a single pass approach with a long contact time, maybe a minute. But then the endurance of the reactor could be hours, and those will be very large, and the reactor configurations will look different than my sludge dewater, which is a much smaller, higher concentrated flow stream. But so ecosystem remediations would be a challenge, but based on the tighter of those ecosystems, we might be at the low end of our application. But the problem with this technology is that struvite is always soluble in water. So we're always going to leak a couple ppm of ammonia and phosphorus. So we might not be doing any net good. But for like highly polluted systems, we can remove those additional ppm very fast, but you'll still need a terminal polishing step. But luckily at our effluent ppm, ion exchange becomes very competitive, and other technologies like chelating of phosphorus or some electrochemical approaches, they scale better at low concentrations, and we can provide them those low concentrations. Hope that answers the question.
Okay, thanks, you guys. Here's one for me, I think. Is this technology available for countries outside of the United States of America?
Yeah,
just real quickly, our patent is a United States patent, so we only have patent protection in the United States. Therefore, we only license to United States-based companies. So that's the first key thing. Also, we require that technologies that are licensed to be substantially manufactured within the United States. So those are two kind of requirements we go by when we license things. It's got to be a U.S. company, a U.S.-based company, and it has to be substantially manufactured in the United States. Once the licensee has the license and they're manufacturing, they can export the technology so long as they comply with the U.S. export control laws. I hope that helps answer that question.
So, Lou, to clarify, does that mean outside the United States they can just copy this willy-nilly?
Well, we don't have protection outside the United States for intellectual property.
But if they do, I'll be sad. So just remember that.
We'll all be. Also, another question here was about recording. This is going to be recorded, and it will be on YouTube. So basically, if you can get on YouTube, you can see this presentation. Griffin, I got a couple of other questions here we probably ought to go through just to help make sure everyone understands. One is, what concentrations of ammonia is this technology designed to handle effectively?
I'll hit that one after you hit up Harold's question. He actually has a good one. He asked it like a couple minutes ago.
Oh, okay, I must have missed that one.
Yeah, I just saw it too. So you want to read it?
Oh, let me see. I can't seem to find it. If you can see it, Griffin, you can ask it.
If you want to specify the NSF stuff, I'll look into it. But Harold asked, what's your experience with biofouling? And all the cycles we've ran, we haven't really seen it. So that's one of our concerns, is that we'll probably have a filtration requirement because this acts as a filter bed. The particles are on the order of 100 microns. They're a bit smaller than ion exchange resins. Our back pressure is a bit higher, but we will filter out junk. So we'll have a filter requirement on the influent, primary treatment. And if biofouling is a concern, my hunch is, thanks for the link, Ray. Yeah, my hunch is that the regeneration is not very nice to the bacteria. So every time we regenerate it, which will be, every couple times an hour to a couple times a day to a couple times a week, the bacteria are going to have a very bad time, because our coldest regeneration is higher than body temperature. The bacteria they're gonna not have a good time. So now, the bacteria will leave like biosolids, like their corpses more or less. That could accumulate. We have not seen it in any setups. A back flush is possible with this setup because we do that to, reset the bed. So there might need to be some additional filtering or treatment and potentially adding of, anti-biofouling components. But we have not seen it. And we think the regeneration, due to it being elevated temperature, kind of mediates the biofouling. But that is a very good question, Harold. And you want to go into your additional questions you got offline, Lou?
I just wanted to mention real quick to Ray. He sent a link for NSF. Ray, if you email me, I can work with Griffin and we can help better answer the question about NSF.
Yeah, and any other email questions, I can give written responses as well.
Okay, Griffin, the other question was, what concentrations of ammonia will the technology handle effectively?
So these numbers change based on like facts, but my preferred range is 100 to 1,000 ppm. It can do above 1,000 ppm. I just don't think it trades as well with other technologies. You know, you get to like 50% ammonia by weight, you could just run steam stripping. Steam stripping does better at higher concentrations. Once you get lower concentrations, it makes less sense due to energy cost. This technology is very selective. It works at these lower to it concentrations, but then you get to 10, 20 ppm where we can remove 50, 75% of the ammonia, but we'll leave 5 to 10 ppm residual ammonia due to the solubility of struvite. I don't know if it's worth running this technology at that point, but 50 ppm getting 80, 90%, that makes a lot of sense, and that's probably good enough. So we can, and even 20 ppm, you might be able to get 75% treatment. So anything between 20 and 50 is more marginal, but I still think it's very possible. And 100 to 1,000, we've easily proven in the lab and in other sites, it works fine. Above 1,000, just it trades the other direction. So those are the preferences. This is as ammonia N concentration. All right, you want to keep going, Lou?
Yeah, I've got one here that also Ray works over in Hawaii with a lot of folks, and there's a lot of lagoons and things like that in Hawaii. So there's some very unique things that he's running into problems with trying to treat places. And the question kind of is, can the system be adopted for smaller scale applications like residential settings or small businesses? You kind of touched on that, but you know,
I would say that's a bridge. So we need to get the control algorithms. Essentially, we instrument highly right now because we're still characterizing the process. Eventually, you can run off timers. If you have a known wastewater coming in, you can just run off flow rates and timers if you have a very consistent wastewater, or you can run a cheaper technology like conductivity to determine the solution, the flow rate solution or the dosing solution. So residential, I think, is going to be very hard because, like, a septic tank just kind of works. It might have a pump, it might not. It just does its thing. It's going to be hard to compete against a septic tank, and septic tanks have their own problems. So, but for small businesses, this technology can scale. ISS is a 6-person household, so it could work for that. But our budget's a bit higher than the average homeowner by about 7 orders of magnitude. So, like, yeah, it could be done, but that's a later. Once it's working in industry, it can probably, because one of the main goals is wastewater treatment. There's 15,000 wastewater treatment plants. Like, it could be decentralized further with technologies like this and allow, we call it local fertilizer production. Because right now, ammonia fertilizer is only made in 20 factories in the country, 20 chemical plants, and they're mostly in the Gulf Coast. Our biggest importer of ammonia is Belarus. And you can imagine that's kind of a problem right now. This technology enables us to recover ammonia from wastewater. It's excreted through our protein metabolism. And it allows us to recover the ammonia. We could recover half or more of the ammonia we get from the Haber-Bosch process. And we don't import much ammonia, but we still import a little bit of ammonia. This is a national security issue. So decentralized fertilizer production also, if transportation breaks down, our fertilizer comes from like the same area of the country. This allows every community or Hawaii to make their own fertilizer, or other countries to make fertilizer that they're not dependent on other people. Because not every country can afford a Haber-Bosch ammonia production plant. They wish they could, but they're a couple $1 billion each. This technology is not a couple $1 billion each. So smaller scale though. So yeah, there's other advantages to that. Cesspools, I like that term.
You see how many he's got? That's
84,000.
That is incredible. Uh, yeah, so I wanted to make sure we address that because I know we've had problems with people trying to use this when the concentration wasn't high enough and it wouldn't really function very well.
Ray, characterize these cesspools. I like the term. Lou, one of the licensees is working on something like that. I think you know the one.
Right, yeah. Just want to make sure people are aware that if you
Yeah.
if you're not within the scale of what this thing will work on, it
Yeah.
doesn't work
And that's
very
the hard
well.
thing. Yeah. Characterize the ammonia and the pH and the phosphate. Magnesium would help too, but not as important. And because yeah, if they're too dilute, we're not the right technology for it. And if it's super dilute, I know a company who could probably do it too. They're experts in this, and I wouldn't say they're like a frenemy, I guess. They're my rival. But yeah, their technology at low concentrations is much better than this NASA one, but at high concentrations, I think I got them.
All
Yep.
right. Okay, we got
Yeah. So yeah, Lou, we'll talk that offline, but maybe we can get them in contact with that licensee.
okay.
I think that was fine.
Another one that might be a good one here is, can you please elaborate a bit more on how the system compares to traditional ammonia removal methods in terms of cost and efficiency?
Yep. So I went over that with nitrification, but our other competitors felt like ammonia. No, nitrification doesn't recover ammonia. We operate on a different access. Someone wants a QR code, Lou. You got to figure that out.
We'll let
But
you worry about that one.
yeah. So with compared to like ion exchange resins, they aren't selective. They're slow. They're kinetically limited. They like to heat up the influent to get higher kinetics, and they aren't selective. They'll pull up every cation besides ammonia with a 10-to-1 selectivity ratio. We're at hundreds of thousand to one ratio. This reaction, there's no competing reactions you have to worry about with calcium or sodium. It just at this pH range, it's the only one that occurs. So it's very useful. But yeah, compared to steam stripping, we're way less energy, and we can also select against organics. When you get this ammonia recovery, it's ammonia and water, nothing else. Nothing else gets absorbed by the media, and nothing else gets regenerated by the media. As long as you run a little rinse before it, there's no organics, no other salt, high purity product, and no, like steam stripping can't provide that. Ion exchange can't provide that. And then our volumetrically, we're smaller, and I'd say we're more complex to operate, but our OpEx and CapEx, when run properly, can be lower than other competitors.
Okay, thanks, Griffin. I think you've already touched on pretty much all the other stuff we have questions on. So we'd be repetitive if we ask those questions again.
Let's see it.
Unless you can think of something else you might want to mention while we still have a couple of minutes.
Oscar, you got anything?
No, not really. Just to make a comparison, this is kind of like a pressure swing,
Yeah. Oscar
The
studies these, yeah.
the loading part is different, but the removal part is
Yeah. So instead of having like absorption based process, this is a precipitation process. So it's reacting and forming like a new chemical, and then it just reverses. But otherwise, me and Oscar treated it like an ion exchange resin or a pressure swing absorber. Ion exchange resins regenerate with alkalinity. We absorb due to alkalinity, but we regenerate with differential pressure and temperature. So it's a very neat process, and I keep reinterpreting what I call it every time I talk about it, because it's nothing's like it, and that's probably why it wasn't discovered.
All right, guys, that's about all the time we've got for questions today. If you have a question we didn't get to, or you have questions that that you'd like to ask afterward, we'll follow up with you by email within the next week if you'll shoot us an email. If you have additional questions, please feel free to email them to me at the address shown here on the slide. And we'll be sure to follow up with the answers to those as well. Once again, we really appreciate you taking the time to be with us today. And thanks, Griffin and Oscar, for your time.
Yeah, thanks, Lou. Thanks, Hia.